Hi everyone, this is just a little introductory page to just introduce myself. My name is Teresa Tang and I am a PhD student at the Sussex Baby Lab at the University of Sussex. Most of my research is spent working with babies and children. Generally speaking, my research looks at infant visual development and colour vision deficiency in children. And as a little bit of promotion for our lab, if anyone has any children from 0 to 16 years old, please feel free to follow us on our social media pages on Facebook and Twitter. We have some upcoming online studies that might be of interest if your children want to take part. So in today's talk, I'm going to be talking about one of my projects called ColourSpot. ColourSpot is an iPad screening test we have developed to test for colour vision deficiency in young children. Before I talk about the app itself, I'm going to give you an intro background to give you an idea of our rationale. So what is colour vision deficiency? Colour vision deficiency, abbreviated as CVD, is a congenital visual disorder which affects approximately 8% of males and 0.4% of females. This graph shows the sensitivity levels for each of the 3 cones in our visual system to different wavelengths of light. So we have S cones which respond to short wavelengths of light, M cones which respond to medium wavelengths of light, and L cones which respond to long wavelengths of light. So normal colour vision is the interaction of the 3 signals of these cones, these S cones, M cones and L cones, whereas CVD is when there is an absence or abnormality of the spectral sensitivity of one of these cones. So there are different types of CVD and they have different names. Tritan refers to a deficiency in the S cone, but this is extremely rare and very few people have it, with a prevalence of about 0.001%. What we more commonly see is a deficiency in the M cone, which we call deutan, or a deficiency in the L cone, which we call protan. And you might hear this more commonly named as red-green CVD. Other sort of fancy terms we use in this world is dichromacy, which is the most severe form of CVD where there is an absence of the L or M cone, and this is much rare at approximately 2%. We also have anomalous trichromacy, which is an abnormality of the L or M cone, which is a milder form of CVD, but also more common at approximately 6%. So why is detecting CVD important? Firstly, there is a lack of awareness. A lot of children are unaware of their CVD, and 50% of people who have CVD only become aware of their condition by the time they reach secondary school. In the UK and in many other countries, there's no routine screening for CVD in schools or opticians, so there are a lot of children out there who have an undiagnosed CVD and they are unaware they have a problem with their colour vision. CVD can also significantly impact people's lives. 90% of adults with CVD report having difficulties in daily life, and these are problems people with normal colour vision might take for granted. So these can include difficulty reading maps, not noticing changes in skin colour such as a sunburn or a mole change, problems when playing sports such as finding the ball or identifying team members due to the colour of bibs, difficulty knowing when food is cooked or ripe such as meat, and it can also lead to negative well-being effects such as the feeling of anxiety, embarrassment and low self-esteem. And it can also cause limited career options, so not being able to work as a pilot or in the army. This makes early diagnosis necessary. Children with CVD are found to be at risk of social, behavioural and emotional difficulties and poorer educational outcomes. Education heavily relies on colour as a learning tool, especially in those early years. And it's been found that 10% of the content in textbooks rely on normal colour vision to solve questions. So this can lead to children with CVD to be disadvantaged in the classroom. And it can also lead to misunderstandings about their behaviour from teachers and parents who might be unaware that a child struggling in the classroom might be a result of their CVD. The reason we have made ColourSpot is because although there are many CVD tests out there, they all have their limitations. So one limitation is problems with accessibility. A lot of tests require a trained administrator and they're expensive and they're not accessible to the public. Another limitation is problems with suitability. Although some tests are catered for children, a lot of them require children's knowledge about numbers, animals and shapes, and this can be more difficult for younger children as well as be unsuitable for children with special educational needs. A lot of tests don't have a control measure, and a lot of tests also have unaddressed general task demands. So if you've ever worked with children, you know that they have limited attention, they need motivation to increase engagement with tests, and a lot of these tests don't actually take this into account. So really, the aims of our study is to 1. Present ColourSpot as a new gamified iPad test for CBD from 4 years old. 2. Use ColourSpot to address the limitations of current tests. And 3. Validate ColourSpot to demonstrate it can correctly classify CBD. So moving on to explain the game itself, children are shown 3 coloured targets, a protan target, a deutan target and a tritan target, and 8 achromatic distractors. The monkey character will ask the child to tap a coloured spot.
Tap a coloured spot!
And when the coloured spot is tapped, an animation appears with a sound.
Well done!
To give you an idea, this is a simulation of how the game would look for someone with normal colour vision compared to someone with a colour vision deficiency. The game also has 5 different scenes to keep children interested and engaged. And here's a video demo of how the game works.
Amazing! Lovely spots! Tap a coloured spot! I love spots!
The game follows a one-up, one-down adaptive staircase procedure where each target, the protan, deutan and tritan target, have their own individual staircase. So what this means is that when a child taps a correct target, the colour of the targets become less saturated, making the game more difficult to play. Whereas if a child taps incorrectly, so they tap a distractor, the colours of the target become more saturated, making the game easier. We also colour calibrated 7 iPad models, and our calibration was successful. There were very small systematic errors, and these are some examples from the iPad Pro, iPad 2017 and the iPad Air 2, which showed the specified chromaticity, which is the outline shape, and the filled in is the measured chromaticity. The advantage of this is that this means that anyone with one of these 7 iPads can play on ColourSpot, which allows colour vision testing to be extremely accessible across the world or in different settings, and it also makes it quite unique from other colour vision tests, which are usually calibrated on one device only. We've also added luminance and tritan noise to account for any individual differences in luminance, cone fundamentals and any small colour calibration errors. So for luminance noise, this was plus or minus 20% of the average luminance. The tritan noise was plus or minus 16% of the background S over L plus M value. So to validate ColourSpot, we wanted to define the best classifications of CBD, so we used 2 independent cohorts. We used a discovery cohort where the objective was to find the optimal CBD classification criteria using an algorithm in that sample. And then next we had a validation cohort, which was to reapply this classification algorithm from the discovery cohort into this new independent sample. And so by doing this, we can see whether we have the same classifications of CBD. So to do this, we had schoolboys aged 4 to 7 years old who were colour vision screened using the Ishihara Unlettered. The Ishihara Unlettered is a plate test where children are asked to identify a shape or trace over curved pathways. The photo here shows you some examples from that test. And so from that, any pupil who passed the Ishihara with no errors were put into an Ishihara control group. Any pupils who made 1 to 2 errors on the Ishihara were classified into an Ishihara inconclusive group, and any pupil who made more than 3 errors on the Ishihara were classified into an Ishihara CBD group. From this, we had a random control group who completed ColourSpot, and anyone who made an error also completed ColourSpot as well. That led us to have these 3 groups, control, inconclusive and CBD, who all played ColourSpot in both discovery and validation cohorts. So moving on to results, each individual data will be plotted to non-parametric psychrometric functions. This is an example of a child's performance in the control group. So each coloured curve is representative of each protan, deutan and tritan performance. So on the x-axis on this graph, it's the saturation level of these targets, and the y-axis is the proportion of targets they got correct. And the size of the targets are also proportionate to the number of trials. So the larger the size, the more trials occurred at that data point. And we can see that for the psychrometric function for this individual in the control group, the protan, deutan, tritan targets all have similar performance. In the inconclusive group, there was a mixture of people who performed similarly with all three targets, but we also had some participants who did perform much worse for protan and deutan targets, as you can see in this graph. And in the CVD group, people performed much worse for protan and deutan targets compared to tritan. And overall, we can see that people in the CVD group have lower thresholds for protan and deutan and can't even get 100% correct on protan and deutan targets when the saturation is at its highest. To find the best classification for CVD, we used an optimal algorithm to search for the best parameters, and it was identified that a bandwidth of 0.7 and a performance level of 21% as a threshold estimate was the best classification for CVD. So this means that at 21% proportion correct is the best threshold estimate to identify who is CVD or who has normal colour vision. So taking the values of protan, deutan and tritan at the 21% threshold, we made a threshold ratio which was the minimum of the tritan over protan or the tritan over deutan. So the lowest number between these two was taken as the threshold ratio for each child. We found that this method was the best classifier for young children because we've used tritan as a control measure here. Many other tests use a cutoff score of protan, deutan and tritan independently, but actually using a tritan as a control measure in children especially is an advantage, especially since tritan deficiencies are extremely rare. By doing this, we can take into consideration of any other non-visual factors that might have affected the child's performance. So for example, if a child was bored when playing the game and is no longer engaged, this measure will give us a better idea to tell apart whether a child has CVD or whether they just didn't engage with the game, in which we would expect them to be poor in all three targets. So when we put those minimum threshold ratios into a histogram, the x-axis here is the ColourSpot minimum threshold ratio, and the colours of the graph represent the Ishihara diagnosis. We also calculate the threshold criterion, which you can see in this line here, which is the boundary between CVD and normal colour vision. And we can see that there's a clear classification in the ColourSpot threshold between Ishihara CVD and Ishihara controls. We do have some inconclusive participants highlighted in black here. If we base their performance from ColourSpot, we can see that some perform similarly to control participants and some also perform similarly to the CVD group. So when we reapply this into the validation cohort, we can see that we still share similar findings. We can see that 100% of those in the CVD group were also diagnosed as CVD by ColourSpot, and 97% of those diagnosed as normal by the Ishihara were also normal by ColourSpot. We do have 3% of participants who were classified as normal by the Ishihara but CVD by our test, and 2 of those are very near this threshold boundary over here, as you can see, but there is one that performs very similarly to participants in the CVD group, and we believe this is a false negative by the Ishihara, but only a genetic test can really answer that question. Excluding inconclusive participants, our analysis showed that the Ishihara CVD group had significantly lower ColourSpot threshold ratios than the control group. So to conclude everything, the take-home message you really need to know from this talk is that ColourSpot diagnoses similarly, if not better, than the Ishihara unlettered test. And we say it diagnoses better based on the fact we can determine the CVD status of the children who were classified as inconclusive. ColourSpot has many advantages compared to other tests. It's a fun, interactive game. It's self-administrative, so it doesn't require any verbal instructions at all. It's highly accessible and can be done in any setting. It's short, it has an adaptive staircase, and it also has a control measure. ColourSpot has a lot of potential great impact and implications by allowing CVD diagnosis by 4 years of age. It can change the way we choose to colour vision screen children, especially given the current situation with coronavirus, and it can also increase CVD awareness as well. So I'd just like to make some acknowledgements, because even though this is my PhD work, this work is a result of a lot of team effort and involves other people who deserve to be credited. So my supervisors, Professor Anna Franklin and Dr. Jenny Boston, as well as Dr. Leticia Alvaro Llorente and Dr. James Alvarez. Thank you for listening.
Thanks for playing ColourSpot. We had so much fun. Bye-bye.